Yeah, so I guess so I want to tell you a little bit about something I've been thinking about recently. So in particular, yeah, I guess well, the title of the talk is Topology of the Dirac equation on spectrally large three manifolds. But I guess the general theme that I've been trying to think about is yeah. So I guess maybe before going to like details or statements or anything, yeah, maybe the general theme is that suppose you have a three manifold, closed, connected, oriented, and I guess I guess the question that I've been thinking about is like you have the geometry of the three manifold and the topology. And for me, geometry is something that depends on the Riemannian metric, and topology is something that doesn't depend on the Riemannian metric. A very, very basic definition of the thing. Yes, and I guess the question is like, can you use Flirt theory, gauge theory to somehow probe the interactions between the two? So if you have a three-manifold Y, can you use the Seiberg-Witten equations? I like to think about the Seiberg-Witten equations. Can you use them as a mean as a tool to connect the geometry and the topology of your space? And okay, so yeah, today maybe I guess the main theory that I will state probably it's something that given topology, it tells you something about geometry, and in particular spin geometry. Okay, let me just give you a very quick refresh on the kind of things that come into play. Yes, in particular, let me just write down the equation just for as a review. So suppose you have your three manifold with a Riemannian metric, then a spin C structure. Yeah, so for me, at a practical level, for me, this is a spinor bundle. This is rank 2 over C plus 2 Hermitian bundle. Okay, and then I have the Clifford multiplication, which is a way in which the tangent bundle of your manifold acts via Pauli matrices in your bundle. So this is Clifford multiplication. Okay, and once you have this, we can look at two objects. B psi, this is a spinor, so a section of this bundle, and B, this is a spin C connection, so a connection that preserves all these structures. And the Seiberg-Witten equations are, a pair of equations that, it's some kind of coupled equation that, relate these two. And in particular, these equations are, the spinor should be harmonic with respect to this connection. And then, there's an equation relating the curvature to some nonlinear term in the spinor. The notation that I use. Okay. Yeah, so here, just as a quick, we won't really go too much into detail. This is the Dirac operator. This is maybe the most important thing that I'll be talking about today. So maybe I'll just, this is the Dirac equation. Yeah, and then, if you have B, then, B induces, it's a connection on S, so it induces a connection on the terminal line bundle. Okay, so this is just a U1 connection. So, now its curvature, FBT, curvature is a imaginary valued 2 form, which is closed by the Bianchi identity. Okay, so yeah. And yeah, these are the critical points of the Chern-Simons Dirac functional. And, Floer homology is, trying to do Morse theory with this functional. Yeah, so I guess, yeah, so these are the equations in general. For the purposes of what I've been thinking about, my whole mathematical life, like I will say. So I'm mostly interested. mostly interested in the case where C1 is torsion. Okay, so the C1 is a first-term class of the spin C structure, and I'm interested in the case which is torsion. And you can think of it. This is interesting because a lot of subtle invariants lie here. Okay, meaning I think non-torsion spin C structures somehow are a little easier to understand in some sense. The torsion is really where the hard and the subtle things in some sense comes out. For example, correction terms, Froshim invariants, they live in they arise from the structure in the torsion story, and a lot of stuff uses torsion in a spin C structure in a very they're somehow some richer from certain point of views. Okay. Yeah. So I guess the fact that it's interesting, of course, usually means that it's also harder, and this is harder because of the following. In the torsion case, is the case in which you actually have reducible solutions. So reducible solutions be 0. Okay. So if you look at the equations and plug in phi equals 0, you see that the first equation is always satisfied because the Dirac operator is linear. In the second equation, there's this quadratic term that vanishes. So the equation just saying that the connection is flat. So we get this kind of correspondence. So reducible solutions when C1 is torsion, be 0 up to gauge. These are the same as flat connections. These are U1 connections up to gauge. And these are the same as a torus. So this is a torus of flat connections. Okay, this is a B1 of Y dimensional torus. Okay, so first of all, this is bad because well, in particular you always have reducible solutions, so these are somehow bad points in your moduli space. So you have to somehow understand how to get get rid of it. And in particular, well, this is always higher dimensional when B1 is positive, so you always need to somehow perturb things in a very careful way in order to define invariants, right? So I guess one needs to be careful when defining Floer homology. Okay, and it's much more hard. It's much harder than the non-torsion case, because in the non-torsion case you don't have reducible solutions. So those are the points that I really need extra care. So that this simplifies things a lot. But yeah, I guess this was solved by Kreimer and Mravka. Monopole Floer homology. Okay, this is a S1 equivariant theory. In which the reducible locus is really the fixed locus of your action. And I guess for today, maybe I'll mostly focus on the group HM2 of YS. And if you're more familiar with Hegel Floer homology, for a torsion spin C structure, this is the same as HF plus of YS in Hegel Floer. Okay, so this is just a very quick, a quick review of monopole Floer homology, subwritten equations, and why is torsion spin C structure and somehow, slightly more complicated to deal with than non-torsion spin C structures. Okay, any question about this? Yeah, so maybe I guess before actually stating some theorems, I want to spend some time talking about a misconception I had. So this is a misconception I had, until spring 22. Okay, so about a little more than 2 years ago. By that time, I spent 10 years thinking about monopole homology, but I guess then I realized I really don't understand anything about monopole homology yet. Yeah, so this is the misconception I had. So, in order to have very complicated Floer homology group, one needs to have a lot of irreducible solutions. Okay, so somehow, Floer homology, you have both reducible solutions and irreducible solutions. And somehow we think of reducible solution as the easy one. So, somehow one will think, oh, if you don't have any irreducible solution, then Floer homology should be extremely simple, right? So here by very complicated, I mean, for example, this is this is a module over, Z adjoint U with degree is -2. And you can think of, very complicated. One can think of, the reduced Floer homology, maybe, the number of generators you need to have, for the torsion part. The torsion part can be arbitrarily complicated. Maybe yeah, something like that. Okay. So yeah, I'll be a little more precise later. Yeah. So I guess maybe let me try to defend myself and explain why I had this misconception. So this is true. This is true in two cases. If C1 of S is not torsion. Okay, so that's in a non-torsion case, there's no reducible solution. So you really just have irreducible solutions to play with. So if there's no irreducible solution, then the Floer homology is trivial. Okay, and then the other case in which this is true is when if B1 of Y is 0. Okay, in this case, what happens is that well, in this situation, you only have one reduced, your torus is really just one point. This is the fixed point of the S1 action. And you have a bunch of irreducible solutions with probably trajectories. But yeah, if there's no irreducible, then this S1 just gives you the tower. So, and usually what happens is that the irreducible, something cancels with the bottom of the tower, and something gives you torsion. But yeah, if no irreducibles, we get that the Floer homology of YS in a given spin C structure, you get that HM is the same as the Floer homology of S3, which is the homology of CP infinity. Okay, so this is just the tower. Okay, so in particular, if for none of the spin C structure you have irreducible solutions, then you're an L space. Okay, yeah, so this is why, somehow in my mind, this will say, oh, if you don't have any reducible solution, then your Floer homology should be somehow trivial. But this is very false already if B1 equals 1. Okay, so this is very false. Already if B1 of Y is 1. Okay, so this might be, extended example. So this is some computation I did in the spring. Yeah, so I just want to describe you some examples of manifolds that actually, it turns out they don't have any irreducible solutions, but actually the Floer homology is arbitrarily complicated. So, so this is, and sorry, when I say there's no irreducible solutions, I mean, after I perturb things, in a way that everything is transversely cut out and everything. So, it's not that I don't perturb things. After I perturb things, there's no irreducible solutions. So I look at this example where, I pick a Riemann surface. Okay, and then I pick, a square root of the canonical bundle. This is what is called a theta characteristic. Okay, so this is a line bundle, holomorphic line bundle that squares to the canonical as a holomorphic bundle. Okay, so you can think of this the same as a spin structure on your manifold. Okay, and then I pick an automorphism of the Riemann surface by holomorphism of the surface on itself. Automorphism such that two things happen. So, phi pulls back L to itself. So this theta characteristic is invariant. Yeah, and the quotient of the surface-based automorphism is P1. Okay, so it's some kind of finite order automorphism. And you can think of, for example, the simplest example is the hyperelliptic involution that fixes all the spin structures on all the theta characteristic on your manifold. So this you can think of this as somehow a generalized hyperelliptic involution. Yeah, then the manifold I consider is the mapping torus. Which is 0, 1 times sigma mod x1 okay, very bad picture of a mapping torus. Okay, this theta characteristic actually gives me a natural torsion spin C structure. Such that two things happen. Torsion spin C structure, maybe let me call it SL, such that for suitable perturbations, there's no irreducible solutions. Okay, so here maybe let me add for suitable transverse perturbation. So this is the perturbation that you can use to compute the Cyberwidth and the monopole homology groups. So there's no irreducible solutions. But HM2 of this manifold with values in for this spin C structure is arbitrarily complicated. Okay, and I'll explain a little bit more about this, but you can explicitly determine the automorphism preserve the theta characteristic, the line bundle, so it acts, maybe it lifts to an action maybe of something double the order to the space of holomorphic sections. So you can explicitly determine in terms of the action of the pullback on the space of holomorphic sections. Okay. Yeah. So yeah, and in particular, this is a finite order matrix. So the eigenvalues will be some numbers in the circle. So in terms of those eigenvalues, you'll get something. Yeah, but let me tell you what arbitrarily complicated means. Arbitrarily complicated means, in general, this is a manifold. I guess I chose this example because this manifold has B1 equals 1. The fact that the quotient is P1 for the automorphism means that the mapping torus has B1 equals 1. Yeah, and in this, B1 equals 1 means that your flow homology, HM M phi SL. This is like 2 towers plus torsion. Okay, and arbitrarily complicated means the 2 towers are there, but they might be shifted as much as you want. And the torsion, you might need as many generators as you want in order to describe the torsion, and the towers might be as long as you want. So it can be arbitrarily complicated as a few module, provided you always have the 2 towers because those have to be there. Okay, so but the 2 towers you can ask them to be at arbitrarily far apart distance. Okay, so this can be arbitrarily complicated. Okay, and the towers, they're towers, but you can shift them as much as you want. Okay, so yeah, so this actually, somehow, yeah, here it is, so I think this was, I was a little surprised, I was surprised by this because, so that's somehow, that was my misconception. And the question is like, where does, there's no irreducible solutions and there's only reducible ones. So the question is like, where does the Floer homology come from? How do you get interesting Floer homology if you don't have irreducible solutions? And I guess the answer is the following. So the interesting Floer homology arises from the geometry of the family of Dirac operators. It's a circle for the S1 family, dB for B in T Y, where you have the reducible solution. It's a circle, and each of them has a Dirac operator. And this, it's a family of operators. So really, the Floer homology comes from the fact that this is somehow interesting. So, and here I mean geometry. To put a contrast with the fact that this family is always homotopically trivial. Okay, so there's something you have the space of operators, and this family of Dirac operators, because you're in a torsion spincy structure, is contractible. But I'm interested in something slightly more refined. So in particular, let me draw. This is my circle. This is my Ty. Okay, so we have this family of Dirac operators, and the most important thing for this family maybe is like this is this, you can look at the spectrum. It's a diagonalizable operator, so you can look at the spectrum, and the spectrum it's some kind of the eigenvalues form some kind of family of curves that go up and down. Okay. Yeah, and the important thing here will be actually to record the spectral flow is where the eigenvalue these operators actually are quite kernel. So in this family, at some point along this circle, you will get some kernel. Okay, so dB has kernel here. Okay, and being homotopically trivial, and actually there's a little more information. You don't just have kernel, you also have a little bit of an arrow telling you, at each point, at a point where you have kernel, the eigenvalue either goes up or goes down. So there's also a little arrow that tells you the direction. So yeah, so you have something like this. Okay, being homotopically trivial means that once you go around the loop, you go up and down 0 number of times, so the whole thing is 0. But the interesting Floer homology arises from the pattern of ups and downs you see. You know that once you go around, you see 0 of them, but going up 5 times and then go down 3 and then go up 7 and so on, that causes there to be interesting Floer homology. Okay. Yeah, any question? So maybe let me write this down. So the pattern of ups and downs gives rise to Floer homology. Yeah, so maybe I guess the lesson that I learned from this is that, you know, Floer homology really it comes from two things. You know, the one is irreducible solutions. You know, when B1 is positive, at least. You know, one is irreducible solutions, and the other is, you know, how interesting the geometry of the family of Dirac operator is. Okay, so what I want to tell, you know, the main theorem I want to tell you about today is some application of these ideas. So application of these ideas to spin geometry. And in particular, you know, I think things are complicated enough that, you know, I think you already got an interesting theorem when you think about the three torus, which, you know, for topologists is like the simplest three manifolds. So, but, you know, geometrically, it's a very rich manifold, actually. So I'll, you know, I think a lot of the things I say, you can talk about them more in general, but yeah, I want just to state for simplicity a theorem about the geometry of the three torus. Yeah, so I guess so maybe let me fix a metric G on the three torus. Okay, so, you know, I guess I was saying, for me, geometry is like you look at the metric properties. Yeah, so maybe let me just give you the definition. So this is in the title. So this is a quantity that I've been thinking about a lot in the past, you know, 5-6 years. So you know, we say that T3G, this metric, this Riemannian torus, is spectrally large if no lambda 1 star. Let me just write it down and then I'll comment on what this means. Okay, so this is the first eigenvalue of the Laplacian on coexact one forms. Okay, so this is, you know, a quantity that's spectral in nature. So, you know, the Laplacian is a you know, diagonalizable operator, and this is its smallest eigenvalue. Yeah, and on the other side, as tilde p, this is somehow a slightly modified version of scalar curvature. So scalar curvature is the trace of the Ricci curvature. So it's the sum of the three eigenvalues that the Ricci curvature has. As tilde of p is the sum of, you know, of these three eigenvalues at each point you pick the least two. So as tilde is the sum of two least eigenvalues of Ricci. Okay, so it's a local quantity. So, you know, on the right side you have a local quantity, and you take the infimum over the manifold. Lambda 1 star is a purely global quantity, so it's not something that you can just, you know, look at the metric and go around and measure it. You know, it's something that you need to solve some PDEs and do it. So it's a very different quantity. But yeah, let me just give you an example. You know, this is a little, you know, this is the main what comes out. But, you know, for example, if, you know, I guess maybe a little more natural thing to consider, you know, if a Ricci curvature is bounded below, and lambda 1 star is bigger than k, then it's spectrally large. Okay, so this, you should think somehow, you know, this is some kind of quantitative version in which this first eigenvalue is big compared to your metric, to your curvature. Okay, and, you know, just as an example, you know, the flat metric, of course, has Ricci, the flat metric. the flat metric is flat, so the right-hand side is 0, and the first eigenvalue is always a positive number. So then of course the inequality holds that any flat metric on the torus, and of course everything here only involves two derivatives. So if you move your metric in a C2 not too crazy way, and so you C2 neighborhood of it. Okay, are spectrally large. Okay, but in general, it's very hard. Even if I give a concrete metric on the torus, it's very hard to tell if it's spectrally large or not, right? So it's about, so we don't really know much about, it's a nice non-trivial set that we would like to know more about, maybe. Yeah. So, but at least it's some kind of. Yeah. So I want to say something about the spin geometry of metrics with this property. Yeah, so I guess yeah.
Can I ask a quick question?
Yeah, sure.
Right, I get maybe you'll motivate this definition more later, but so the 1/2 in front is because you're taking two eigenvalues?
Yeah, I guess well, no, it's just what the best guesstimate you get, I guess. Yeah. Yeah, I guess you can put with a 0 also with a 1, but yeah, this is a stronger estimate. This is a slightly larger class. Yeah.
Okay. See.
Yeah. It's a negative thing. So yeah. Yeah. So I guess actually at the beginning in the first paper I thought about this kind of things. I proved the estimate without the 1/2. But then we can actually refine it to prove it with a 1/2 in front, which is a stronger thing.
I see.
Okay. Yeah. Thanks. Yeah, it's a very weird looking expression, but it's just some kind of quantitative measure of how spectrally large the manifold is. But that's the one that works out with the estimates in Sever-Witten theory for some reason. Yeah.
Is it so that the motivation is that this is the sort of inequality which is compatible with Sever-Witten theory?
Yeah, I guess what this implies is that if you don't perturb the equations, this something like this doesn't have irreducible solutions. Yeah.
I see. Okay.
Yeah. I'll say more about that. In a bit. Yeah, but yeah, after stating the theorem. Yeah.
All right. Thank you.
Okay. Yeah. Thanks. Yeah. So by spin geometry, I mean I want to study the Dirac equation. So yeah, but to state an actual theorem, I need to perturb things. Otherwise, things might be too degenerate. So let me just fix a section of at each point I fix a self-adjoint map. So I section of IS, so IUS. Okay, and then consider the family of perturbed Dirac equations. The B psi is A psi. Okay, where B is in my torus of flat connections. Okay, so really, one would like to state the case where A is 0, but you cannot say really anything too nice about it. I'll say a little more, but this allows you to prove a pretty statement, I think. So this is the following theorem. So yeah, I'm not looking at a specific equation, a specific B. I'm looking at all of them. Okay, that's maybe the main point of this theorem. So this is I recently posted this to the archive. So if you have a torus which is spectrally large, T3 G spectrally large, then for any this perturbation A, which is just a section of you can think of a 2 by 2 symmetric, Hermitian matrix at this point, which is small and generic in some sense. You can look at the locus K, which is the locus where of B's, such that my equation has non-zero kernel. So this is always a hyper. This is my torus of flat connections. For generic A, this is always a hypersurface, a smooth surface for some general transversality reason. The theorem is that this is actually diffeomorphic to a sphere. Okay, so I cannot say anything about any specific solvability of each Dirac equation, but if you look at all of them, the locus where you have kernel is some sphere. Okay, this is my K. I guess this is not a very good picture, but it's a sphere. There's no holes. Yeah, so maybe you might wonder, it's a kind of a weird theorem. In some sense related to, I guess, there's all these theorems. One way I think of this theorem is like a one-dimension up version of these theorems in algebraic geometry that tell you where the space of line bundles, the theta divisor is where the del bar operator has solutions, these kind of things. But yeah, from a purely to give a little context to this theorem. So if the metric is flat, then you can pick A to be just a multiple of the identity for some delta small, different than 0. Then you can actually check this directly. The things are so explicit that you can just write everything down. All the Dirac operators, compute the kernel, and you can see that that will just be a nice small round, an ellipse, a small ellipse around the point. Okay, so this is the case. Yeah, and this also, the flat case also tells you why you should pick some kind of A generic. Because if delta is small, if delta is 0, then K is only a point with multiplicity 2. So here, everything around K in the red picture will have multiplicity 1. But yeah, in the non-generic case, things might be a little worse. So if you're in a non-generic case, things might be non-degenerate. So you cannot really say anything about the smooth topology of this locus where this equation has solutions. But yeah, if you're in a generic situation, then you can actually say things. So this is somehow maybe the motivation for why this is true. Yeah, and I guess the idea is that metric G is flat, so it's nice. You can expand everything in Fourier series and do computation very explicitly. Yeah, a general spectrally large metric, you cannot do anything like that. So you cannot use you won't be able to explicitly describe this K, but you can still say that it's actually diffeomorphic to a sphere. Okay, and maybe let me just as another motivation, is that for any so here I have two, my inputs are two things. The torus is fixed, but I have the metric and the small, this small section. And if you pick any GNA, there is this hypersurface non-empty. Okay, so independently of how you choose your metric and perturbation, this subs in general will just be a subset, won't be non-empty. This follows from the Atiyah single index theorem. And it really follows because the triple cup product of the torus is non-trivial. Otherwise, this family would be trivial. But yeah, in general, even if for generic thing, you'll get a hypersurface, but in general, it will be an extremely complicated hypersurface. We cannot even say, in general, you can write down things with arbitrarily high genus and things. So yeah, really these conditions, really are necessary for proving a theorem of you have a sphere of place where you can solve this equation. Okay. Okay. Any question? Yeah, so I guess maybe.
Sorry, I was slow hitting my unmuting myself. So how are you getting that from the TS? That's from the families, some families index theorem?
Yeah, so the family. So if K is empty, then all these operators are invertible. So the index is 0. So then the triple cup product has to be 0.
Okay.
Yeah.
Thanks.
Thanks. Yeah. So just it's a algebraic topology. It's a concept. Yeah. Thanks. Yeah. So I guess maybe the why the reason why I like this theorem is that the statement is a statement purely about linear operators. So Dirac operator is linear. I just look at a family of it, and I look at where it's a family of operators, linear operators, and then see where it has kernel. The proof actually uses nonlinear things. So it uses the Cyber-Witten equations. If you want to prove something like this, something more specific. I guess linear things like index theory, they are very unlikely to be able to get you to statements like this. So it's really like some nonlinear input that's key in improving these things. Okay, so maybe let me just give you an idea of the proof. Okay, and I guess maybe the general idea is that the thing I was saying before is like, I think Floromology, I guess my misconception was that these were just irreducible solutions. But, it's also plus geometry of the family of Dirac operators. Okay, so, I guess this is, the lesson we learned from the examples that I gave you before with the invariant theta characteristics. And the idea is that, if you are somehow in a situation in which you can say that there's no irreducible solutions, then somehow you can use Floromology to say something about the geometry of the family of Dirac operators. Okay, so in order to say that there's no irreducible solution, this is from the work with Lipnowski. So KT. So if you have a metric which is spectrally large, for any B1, then the unperturbed Cyber-Witten equations do not have irreducible solutions. Okay, so it's really important here, unperturbed. Once you perturb, I guess once you perturb, things get much more complicated. So I won't get into the details of things, but one thing that, when B1 is positive, when B1 is 0, this implies that, Y is L space. And here it uses the fact that perturbation is not too hard in this situation. Okay, there isn't really much to perturb. Your reducible solution is just a point, so you just need to make sure, that point, the Dirac operator there has no kernel. and then the spectrum becomes simple, but that's not too hard to arrange. Okay, so a spectrally large manifold with B1 equals 0 is automatically a null space. But yeah, when B1 is positive, it's much more subtle. And in particular, it's subtle because, yeah, you have these extra directions that, these estimates are somehow, the estimates that one uses to prove this theorem, spectrally large, it's somehow robust. But the issue is that it only is only concerned with coexact things. So when one is positive, you have the harmonic directions. And in those directions, you cannot really perturb. But then those are really the tangent space of the torus. So you want to get rid of those. So it's much more subtle because you need to get rid of the torus of flat connections. And if you pick a general perturbation, this result that holds for an unperturbed equation won't work anymore. So if you perturb in the wrong way, irreducible solutions pop out. It's much more subtle. So we need to get rid of Ty. Okay, but this Ty is bad because the tangent spaces are the harmonic directions, and those are the ones for which this theorem doesn't work anymore. So you have to work a little harder. So I guess the idea is that so one needs to perturb the equations carefully in order to achieve transversality without introducing irreducibles. And yeah, that you cannot always do. You have to be a little careful. Even if the unperturbed equation don't have irreducible solutions, if you perturb a little bit, you might get irreducible solutions. So, and for our general strategy, we don't want irreducible solutions. So as to be able to relate Fleuromology with the geometry of this family. Okay, so the idea, it's not too, maybe let me just write down the kind of perturbation one uses. Yeah, so you have the usual Chern-Simons Dirac functional. Then I'll add this perturbation, a perturbation that looks like this. This is the A that I used to in my family of equations, and this is just so that along the reducible locus I really see that family of Dirac equations, perturbed Dirac equations. And then I add a perturbation that it's a kind of a Morse function on the, so it's nothing too original. This is a Morse function on torus, so f has to be a carefully chosen Morse function, f from Ty to R. And if you pick a random Morse function, you will actually introduce irreducible solutions. You have to choose a Morse function very carefully in a way that depends on the locus where my Dirac equation has solution. This will be some kind of hypersurface, and I have to choose. In general, it would be disconnected. Yeah, so I have to pick a Morse function which is takes into account the shape of K. So that's how also I will somehow extract information. Okay, and if you do this very carefully, you can actually write down the a chain complex which doesn't have any irreducible solution. It only has your reducible solutions, and then from there you can use this to relate the Fleuromology group to the topology of this hypersurface. Okay, at least in simple situation. Okay, so when B1 equals 3, in the case of the torus, for example, the thing is already complicated enough that I don't know how to write down the differential, actually. I can only write down the generators. But the situation is still simple enough that from the Floer homology, you can extract something about the topology of K. So in particular, in our setup, we have the Floer homology of the torus with the standard trivial spin C structure, and we're lucky that it is not too complicated. I guess we're lucky that it's neither trivial nor too complicated, so it's right in the middle where you can actually say things. And then using, I don't know how to actually describe the chain complex, so really you use some kind of spectral sequence arguments or some kind of algebra, so to get actually the topology of this thing. Ty3, Tt3 is a sphere. Okay, and I think it's a good place to stop. Thank you very much for listening.
Okay, I think we can probably thank Francesco and then ask some questions if we have more. So this is taking me a little bit to process. I think it's very cool. Are there questions?
So can I ask, so the example you gave where you get interesting things was, so it was the mapping torus of something like something like a hyperelliptic involution.
Yeah, any finite any finite order automorphism, or any finite order mapping class essentially.
Yeah.
Such that the quotient is P1, yeah.
Yeah. So can you do that with, I mean, suppose you wanted somehow, hyperbolic manifold with this.
Oh, so, yeah.
So suppose you took something that had, I don't know, similar action on cohomology or but was maybe pseudo-Anosov, so you actually had do you get similar results, or is it depends on, you really need to know?
Yeah, it really, it's much harder. Here I really use the fact that the mapping torus has a metric which is locally a product. So I take a product. I guess the it's finite order, so it fixes there's a metric.
Yeah, there's a preserved metric. Yeah.
And I take the product, the metric which is product invariant, the product metric. And that allows you to boil down the equation to, this family of Dirac operators becomes essentially becomes the theta characteristics on your surface. Yeah, in general, if your metric is the hyperbolic metric won't have any kind of this kind of product structure. So it's a intrinsically three-dimensional thing, and it's much harder to say anything. Yeah.
But it seems like it might be interesting to try to do it anyway.
Oh yeah. Well, I would love to be able to do that, but
okay.
I guess those metrics are super complicated. So
Thanks.
Oh yeah, thanks for the question.
Just one question. I think I may be lost the punchline, but what does the fact that it was a sphere as opposed to something else? How did that? What was your calculation? Or is your conclusion that the Seiberg-Witten solutions are related?
Oh, I guess the idea essentially is that if the rough idea is that if the hypersurface wasn't a sphere, then the Floer homology would end up more complicated than it actually is. Essentially, the Floer homology of T3 is just 3 towers like this. So there's 3 towers like this, and there's no reduced Floer homology. And essentially, what you can show is that if you don't have if this locus where the Dirac operators has kernel is more complicated than a sphere, then you have somehow more complicated Floer homology. So you always have the 3 towers. Maybe they end up at different ends, or you get some reduced Floer homology. So there's some kind of argument like that. So really, all I need as an input is the Floer homology of the 3. So this theorem actually works for any manifold which is has the same Floer homology of the three torus as a module over the cohomology ring. But yeah, I don't have any other interesting example where it's spectrally large. So I guess it applies to the three torus because I only stated it for the three torus because of that.
Can you rephrase this theorem in terms of couple Morse homology here, like for Jacobian three torus?
Well, couple Morse homology is really about the localized version. Yeah, couple Morse homology. So here, I will only be looking at the stable critical points. I guess the main problem is that the chain complex, even if you're only looking at stable critical points, so only reducible critical points, the chain complex actually takes into account irreducible solution as well. So that somehow exits the realm of couple Morse homology.
Okay, I see. Right.
But yeah, the localized version, yeah, once you localize, you get couple Morse homology, and that only depends on the triple top product. So yeah. But yeah, in some sense, yeah, most of the chain complex is just couple Morse homology, but there's also some extra things that come from irreducible solutions that, yeah, they're not accounted in couple Morse homology.
Right.
Yeah. So yeah, you can't a lot of solution coming from couple Morse homology, but you can't something else as well. Yeah.
So like the set K contributes something to the irreducible part.
Yeah. So the set K really. Yeah, I guess I didn't. Yeah, I guess the choice of the Morse function, really, it's about the choice of the Morse function that comes into play. So here, for example, you need, essentially you need a critical point in each of the intervals. So once you look at, you essentially need, yeah, the more complicated K is, the more complicated the Morse function you have to choose is, and the more complicated the chain complex will become. Yeah. I don't know if that answers your question.
Yeah,